All right, I think we can slowly start. Hey everyone, welcome to the deep language learning tutorial, modeling language from raw speech. We're gonna have 3 hours today to talk about all the things that we prepared for you all. Um, so let's just start with some basic logistical things. Um, we have a website for this tutorial, which has a slightly long URL. But if you go to the program's website, LSA program's website, and you click on our tutorial, you're going to see a link to this website, which is going to be very useful if you're interested in doing and following along with the workshop. So the website features some useful stuff. First, it features the slides that we're going to be using on this link. And then also importantly, it features all the collabs that we prepared for the more hands-on part of this tutorial. And we'll try to upload some recordings as well. There are some videos, there are some resources. For example, if you click on the resources, you'll get some links to the papers and descriptions of what this tutorial is all about. In the videos section, you'll see quite some videos about the stuff that we're going to be presenting today. And yeah, so that's one useful thing. The other useful thing is we want to introduce ourselves and who we are. So the people's section of this tutorial. I'm Gaspar Begish. I'm an associate professor at linguistics at UC Berkeley. And I have a great pleasure to be joined today by two amazing scholars who are responsible for several aspects of this work and with whom we recorded several papers. So Alan, you want to say hi and introduce yourself?
Yeah, hi. I'm a PhD student at Johns Hopkins in cognitive science, and then before that, I was an undergrad graduate in calculus, so that's where a lot of the work. I'm Bruno. I'm a PhD student at Brown, working on computational phonology testing.
All right, so we also have two other students who couldn't be here today. Jingyi Chen, who's a PhD candidate at the Ohio State University, and Sneha Ray Barman, who is also a PhD candidate at Indian Institute of Technology in Guwahati. And we're going to be playing their talks later in the part two of this session. But they also produced amazing work in this area. So it's like a collaborative thing. Also, we want this to be a discussion, very low key. So feel free to jump in with questions and remarks. And I think the idea is that we just explore this area, which I think is fascinating together, and see what can be done in the future and what has been done and how to do it importantly. Okay, any questions before we get into the basic ideas behind the work that we do? But if not, we can, I guess, start. So what is this line of work all about? The idea is that we have AI now, and it's performing really well. And the most of the commercially applicable models are LLMs, and they're not learning the way we humans learn language. So what we try to do in our lab, what our mission is to build as realistic models of human language learning as possible. And that entails a lot of things, and we'll go over them step by step, but that's the main goal, to build with deep learning as realistic model as possible of human language learning. And that's why we call this deep language learning. So the landscape currently is right. So we have LLMs and they're producing a lot of interesting work, but they're not very good cognitive modeling models. They can basically test what can emerge in an artificial intelligence, in neural computation, and not as much how things emerge. So what we want to do is we build more realistic alternatives to simulate human learning so that we can actually say, oh, this is how things can emerge in a fully connectionist model. And then that can tell us how we're similar and different, right? So no baby learns from text, no baby learns from massive amounts of text, so our models have no text. We just throw out the text, throw away the text. Babies learn from production perception loop. They listen and they speak, right? Crucially, so any ecologically valid model of human language learning will have to have that aspect of production and perception as well. And there needs to be communicative intent. So how do we learn language? It's a complex process that includes a lot of things, a lot of raw audio and a lot of brain stuff, right? So I have some information in my brain, and I have learned to move my articulators so that they produce sound, so that that sound has that information, and the sound travels to your ears, and you turn it into electric signal again, and you decode my information. So if I say a red apple, and you hear this, and you imagine a red apple, we've probably communicated successfully. So at a very conceptual level, we've created this set of models that learn in this kind of way. And a couple of things that are super important to us is information exchange through raw audio, unsupervised learning, and imitation, okay? So what we do is we used a family of deep learning models that are called generative adversarial networks, which is the only architecture in deep learning that learns by imitation, not by replicating data. So if you take a transformer or LLMs, they just predict the next word in a sequence based on seeing a tons of sequences, okay? If you take a look at autoencoders, they take input data, they shrink it into a small area or small vector, and then they have to expand it, and the input needs to match output, okay? So it's replicating, so it's copying in a way. GANs are different, and they're fabulously different in that they never see, the network that produces data never sees the data. What it does, it needs to create internally a system that will create data such that another network will think it's real data. So it's basically learning to fool another agent into thinking that its outputs are real, okay? And so this is the main principle. If we look at the three networks that we're going to be working with today, we have the G network, or the generator, that has two objectives. It needs to learn to generate speech, raw audio, and it needs to learn to do so informatively, right? So our language is informative imitation. So we hear language of our caregivers and we try to imitate it, and we do that informatively, because if it wouldn't be informative, then it would not be useful, probably. So we have this relationship between the generator and the discriminator, the D network, that forces imitation. Basically, you have a generator that learns to say words such that a discriminator will be unable to distinguish real words and generated words, okay? So we'll go into this relationship in a great detail, but it is a really unique architecture within deep learning, and a super important one for when you model language learning, because we know that imitation is very important in learning, right? If you think of what we do as humans, we need to learn to move our articulators so that the sound we produce approximates very closely to what we hear from our caregivers, right? And this is a very difficult process, but but this is how we try to emulate it with these networks. The other aspect is informative, right? So we have imitation, but it has to be informative for language to happen. And so there's this relationship between the G and the Q network that enforces the informativity, okay? So this G network needs to learn to generate raw audio words such that they carry information. Just as when I said red apple, it carried some information, you were able to decode it. This guy needs to learn to basically construct internal grammar so that the information it'll produce, the sound it'll produce, will be decoded by another network, right? So these G generator and the Q network communicate with each other and exchange information with each other. Okay, so that's at the very conceptual level. We'll go into details behind this, but that's the conceptual level of our architectures. Any questions so far? And feel free to interrupt me, and yes. Yeah, well, that's a great question. What kind of data do we have? We'll show that when we get to this figure. Okay, it's a little bit more complex. But keep in mind some of the things that this architecture brings: imitation, imagination, because the network never actually sees the data and needs to produce it, by imagination, and then innovation. Innovation is super important. That's how babies learn, and basically these models are super innovative. Okay, in a more detailed way, how does our model look like? So we have the generator, right? The network that needs to learn to generate data that takes some small vector of length about 100. Okay, so it takes 100 variables, and through a series of so-called convolutional layers generates data. Okay. In our case, in the most advanced case of our model, it generates EMMA movement, okay, movement of articulators. And those EMMA movements result into sounds, right? So we try to be as realistic as possible. And so we even have the articulatory component in these networks. But the idea is that the generator generates sounds, words, and that those words get sent in the discriminator, again, that needs to distinguish between reals and fakes, okay? The discriminator sees the actual training data. It sees timid words, okay? Or you can take any data that you want, and we'll see Sneha and others have taken, say, other languages and have trained them on other languages. You can basically take whatever data you want and see what the network will learn about that data. In our case, we started with timid because timid is easy. And so the discriminator needs to distinguish between timid and generated data, okay? And during training, right at the beginning, discriminator is very good because it's easy to distinguish between reals and fakes if the generator just produces noise at the beginning because it's not trained. But in time, the discriminator becomes worse and worse at figuring out what is real and what is fake. And our generator becomes better and better at generating realistic data. Then we have the Q network. So this is the imitation part, right? So in a more detailed way, we have a generator takes a small number of variables, turns them into sound, and that travels to the discriminator that forces imitation, and the Q network that forces information exchange, right? So because in those small vector that the generator takes and turns into data, part of those, some of those variables are the so-called code variables that can be representative of information, right? So in information theory models information with, say, binary codes, and that's what we did. So we have one hot encoding or binary code that the generator turns into sound, and then that sound travels to the Q network, mimicking our perception. And the Q network sees this word, sees this sound, and needs to figure out the unique code that the generator had when it was producing a sound. Okay? So basically, it's turning 100 into a word completely in an unsupervised way, in a completely automatic way. And then the perception aspect of this model takes a word and turns it back into the code. So you see that now they're playing a game, basically, of encoding and decoding, right? Okay, so I'm sure you have a tons of questions or not, but now is a good time to ask them if you do. Because we want to get into like the actual architectures of this. Yes.
I'm curious if the visible model introduces some artifacts that aren't present in the training data, or is that some issue with this training process?
Yes, so the physical, this is the most advanced model. A lot of the work we do is without the physical model. The physical model is nice because it's the most realistic one, right? So what it does is it takes Emma and turns it into waveforms. There's nothing cognitive about the way our mouth, the way sound propagates and creates words, right? So what this physical model is basically not as exciting. It's just there to turn Emma into sounds, and it's not trained during training. We pause the weights during training. But if you think of what speech is moving articulators so that the sound they produce mimics what you hear from the environment, right? So it's striking how different, like production is very different in modality in humans than perception. And so we were trying to model that. In terms of artifacts, there's a layer of complexity that adding articulators brings, but in principle, it should work in a similar way. It's a big engineering undertaking, but not as much cognitive undertaking to add articulators.
The performance of this physical model is sufficient that the discriminator doesn't just learn to detect.
Well, we're still working on that part. The problem is that the pre-trained physical model is trained on a single speaker, whereas discriminator hears a lot of speakers. So yes, if the discriminator can have that ability to deal with that, but we were able to get it in the latest model. We were able to get it to work okay.
The goal of the generator isn't, it can still learn even without completely fooling the discriminator. So it still shows like patterns of meaningful linguistic phenomenon, even if there's an artifact that the discriminator can detect. The way the training works, it can still optimize in other ways in spite of artifacts.
Any other questions about the technicalities? What are the dimensions of here? Yeah. It's just 100 numbers. 100 numbers. A couple of them are binary codes or one-hots, and the rest is randomly, uniformly distributed variables. But they're very important.
Yeah.
Yes. Yes. Very important. We're gonna get there. Okay. Good. So we can basically model language, a lot of language learning, a lot of aspects of language learning from raw data. We'll go step by step from phonology, morphology, morphophonology, syntax, and so on. And this is all in unsupervised way. There's nothing, you never give any labels, you never give any text. All you give the model is a bunch of raw audio. And we'll see in the collab set part of this session, it's very easy to train these models. All you need is a folder of audio, whatever audio you want the network to learn from, and then you can test it, what it had learned, and play with it. And we're going to see how we can play it with these models. Yes?
Do you have any program to incorporate like external things that need to us? Audience like learning is odd.
Yes, well, that's coming. We're grounding in vision. Hopefully preprint will be there in 2 weeks. Cannot promise it. Yeah, I have a slide on this later on, where we add vision to these models, but we want to focus on you know, the linguistic aspect first without the meaning, and then moving on.
Well, I'm gonna synapses would say that's part of it.
Yeah, oh, no. Yeah, maybe I didn't mean to say that meaning is not part of linguistic, but more the core, maybe phonological aspect of these models first, and then we go on to semantic. For now, all semantics there is for now is going to be the information in a very rudimentary form, which is one hot or binary codes. So the models are fully unsupervised. They learn by imitation, imagination. They have production perception loop. We have the mouth. They have communicative intent because they need to encode information. And what we'll see is that the disentangled symbolic-like representation emerge really neatly in these models, which allows us to do linguistic modeling. And also, we're going to show you that because these models are interpretable and they're CNNs, they're more similar to the brain, you can really look inside them and compare them not to humans, not only behaviorally, but also in terms of neural computation. So we're going to give you, taste of what these models can do in terms of language acquisition, phonetics, phonology, morphology, syntax, semantics, production perception, articulation, articulatory modeling, language change, and then also comparison between the behavior and these networks and the brain signals and these networks. So this is the basic idea behind this tutorial. We're going to go over this somewhat fast and over some of these because we also wanted to show you how to actually train these models. But the idea is that you can do a lot of work, a lot of work in linguistic modeling with these models. Okay, so we kind of introduced how these models operate, and now we want to see how can we use them for linguistic research, right? And the first thing we did is we tried phonetic learning, right? This is the easiest, simplest thing you can do. And we're going to see how exactly the latent space works and what it does and how we can use it to analyze data. So we take a simple English rule, the simplest there is, which is aspiration, deletion in the presence of S. So English aspiration rule, we say pit, but spit, right? So we delete aspiration when S precedes. And so that's like a simple, phonetic phonological rule of English. And it's a very useful one to test, to illustrate how these models operate internally and how we can use these latent space, those 100 variables, to show that disentangled representations emerge in these models that can be very, very useful for linguistic modeling. Okay, so what we did to model this rule is we took Timid and trained a model on lots of STV and TV clusters, right? So PA, SPA, P, SPI, and so on, to see if the network learns, if the network is able to learn to replicate that rule. And so you throw a lot of data you just have a folder, you have data, whatever you want, whatever shape of the data you want, and then you train the network and see first what kind of output it produces. What kind of output it produces, and this is one example where the network produces a rule pa versus spa, and you see when the S proceeds, the VOT is shorter, and you can behaviorally test that. Basically, you can treat these models as human subject in a way, because they'll produce data, right? This is all generated data. The network generates waveforms. They look very realistic. You can listen to them, and you can analyze them phonetically, just as you would on any human data. And you show that if the network produces an S in the output, VOT is shorter. We're getting there. We're getting there. Yes, yes, that's going to be the next thing. So VOT gets shortened in the presence of S. That's just, a very simple phonetic thing that the network has learned. So what is more interesting actually is, I mentioned at the beginning that these networks are very innovative. And those innovations are super, super informative and interesting. So the network does shorten VOT when S proceeds, but in some cases, it produces this extremely long VOT when S proceeds, right? So in about 12% of cases, it produces longer VOT in the S condition, longer than any of the training data, right? These models are very innovative, and they innovate in kind of predictable ways, because this is what you would expect happens if the model fails to fully learn the rule. And that's what kids do a lot during acquisition. So kids start with long VOT, then they shorten VOT, but in the S condition, there's a period where they haven't learned the phonological rule yet. So a lot of the times there's acquisition research showing that kids do a lot of spa and sta. I don't know if this will play. No, but the network also produces this spa outputs that are nice because they are longer than training data, right? So this is timid. As I mentioned, we trained a network on VOT on timid, raw audio, of course, and the longest VOT in the S condition in timid is, I don't know, 70 milliseconds. The network often violates this distribution and produces long VOT because it kind of hasn't learned the rule fully yet. And again, this is nice because the kids do that as well. What you can do here, just as an illustration, is you can basically treat these networks as agent in a sound change simulation. And so this is where we kind of combine this idea of iterative learning and GANs, and we combine those two. And so you can have one GAN produce outputs and another GAN being learned being trained on those, not on timid, but on the outputs of the first generation GAN, and so on. And so we have shown that basically you can model this gradual phonetic change that looks a lot like sound change with these models in this kind of iterative learning tasks. Okay, so this is basically an illustration of the low-level stuff you can do with these networks. So what we want is to see how symbolic rule-like operations emerge in these networks. And to do that, we go to the latent space, right? So we have 100 latent variables. They're super interesting because we've shown that there's a lot of disentangled representation learning that happens. So again, we have a latent space, 100 numbers from -1 to 1 that get randomly chosen, that gets transformed into audio, raw audio, through a series of convolutional layers. What we do is basically we can take outputs, annotate them for any linguistic property you're interested in, and see which of those 100 variables correspond or correlate mostly with that variable that you're interested, right? So when we train the model on STV and TV sequences, like spa and sta, or ta, pa, ta, the most prominent thing you can test for is, say, presence of S, right? So how does the network encode a presence of a sound that we know is a phoneme in English, S? And what you do is basically you annotate a lot of outputs for S, and you use regression to see which one of these latent variables will light up more in regression, right? So this is what you do. You annotate S, and regression tells you, oh, 11th variable or 12th variable or whatever variable most corresponds with an S. So that's great, but that's not all there is to it yet. The cool thing about this is that when we did this work, our regression technique told us 11th variable is most predictive of S. Now the thing is that these models' relationship between 11th variable is linear. Okay, so when Z11 is closer to -1, there's going to be a lot of S's. When Z11 is positive, there's going to be very few S's in the output. But the thing is that this relationship is linear, although it didn't have to be. So what we did is basically we try to see what happens if you take this single unit and stretch it to extreme values outside of the training range. And this is where we found that this single unit, single neuron, or single variable in the latent space causally corresponds to presence of S to a very nice degree that you can just take that single 11th variable and basically stretch it to extreme values and make S appear or disappear. Okay, so for example, when you set Z11 to -15, almost all outputs will contain an S. But it's even better than that, where you actually take Z11 and gradually interpolate between very negative value and very positive value, the S will just disappear from the output. So the network uses one single variable or a small subset of variables to represent a phoneme or to represent a feature. Actually, Jingi did work on French nasalization, and they found the network uses 2 variables to represent nasalization out of 100, which is nice. And they can do this as well. They can turn they can take a variable and make output be nasalized or unnasalized. And that is what allows you to do a lot of modeling, linguistic modeling. So taking a single variable and stretching it to extreme value, basically, you now have a way to force the model and to work test the models and test how they learn interactions between processes in language. I'm not okay. So this is the basic idea. We have a few techniques to do linguistic modeling so far. Are there any questions or remarks or suspicions so far? Yes. Yes.
This way, it didn't have to be this way, or could it have been the case that the phoneme is represented as probabilistic activation across multiple?
Yeah. That's an excellent question that I don't have an answer to. I mean, I think the null hypothesis would be there's a more distributed representation and not more entangled representation. And I think I don't have a good answer to why it's so disentangled, other than it is and has been, we have found this disentanglement over and over and over again, not only in humans, but also in whales, when we train these models on whales, or like on non-animal communication. These models, you can think of them as extremely smart pattern recognizers, right? And I think that's what also humans are, and that's why we are good at language. But it's nice that we have these disentangled representations, and we'll see a lot of linguistic modeling is possible because of those disentangled representations. Do you have any thoughts on this? Okay, so other things that, oh yeah, sorry, Max.
I was thinking, you also mentioned initialization in French.
Yes.
And that interesting feature on.
Yes.
So you get different sorts of, like, different,
Yes.
different steps sort of along the scale of granularity, right? From like a single feature.
Yes.
A phony. What you're saying is there are two different variables and the two different neurons that corresponded to visualization. Also, like both of them were activated, or did the model learn the visualization of sound out as like a different feature from the visualization of out, right? And that sort of then be an imperfect case of learning.
Yeah.
So they use the model to learn visualization as corresponding to a single neuron maybe.
Well, that's a good question, actually. So I think even the fact that that 2 out of 100 variables encode nasalization, I think that's to me very disentangled. But I agree, that result is even better because it's a phonological feature. We'll play the recording of the talk that will present this. This is not my work. This is actually external labs work. But the nice thing is that French nasalization was learned in a compositional way, whereas English nasalization was learned in a non-compositional way. So in other words, when you manipulate those nasalization variables, those two, in French, you get compositionality because in French, nasalization is contrastive, and in English, you don't. So that's another nice result. Why there are 2 instead of 1? Again, it's a similar question. I do not know, but those are all the questions you can ask when you do this kind of work. Okay, so to move forward, this is our architecture, okay? And other things that can be learned. I mean, the models can do much more than just learning English aspiration rule. They can learn words, for example, in a fully unsupervised way. So remember, we have a network that takes code variables and latent and Z variables, so code and random variables, and turns them into sounds. And you take a few words from Timid, 6 to 100 tokens roughly each, and you give that to the folder, you train the network and see what they will learn. You also give the network, roughly equivalent number of codes, and see if the network learns to encode, to basically use those codes to learn words, okay? So we have ask, carry, dark, greasy, like, suit, water, near. Those are intimate words. We give the network with about with 9 latent codes or 1 hot vector. And see if the network is able to match unique information, 1 hot codes with the words. I mean, the network could learn anything about these words, right? It could learn gender encoding, it could learn length of words, it could learn anything. But the only thing that the network needs to do is to be informative. And the nice result is that informativity is a good enough condition for word learning. Okay, so the network learns to pair each unique code, right? So it gets 100, 010, and 001, for example, with each unique word. And you see here each 1 bump per word when you test that. Another cool thing is that based only on 8 words that the network learns, it learns to produce new words that it never heard before because they're innovative. And they learn from 8 words of English, they learn enough about English phonotactics to create new words. For example, it was trained on ask, carry, dark, greasy, like, suit, water, year, and it says star, dust, carrot, and so on. So that's nice. And the cool thing is that the network, it never even saw the SD cluster before. It learns enough about phonotactics to put these things together in a raw audio form. and also said start, right? It doesn't know what a word is and what it isn't, right? It doesn't know that start is an English word and start isn't, but they're both phonetically plausible English words, and it creates this innovative output. It was kind of nice when we had a transcriber, like phonetician, transcribe these outputs, and I didn't, you wouldn't expect this innovative outputs at all, but the phonetician started transcribing new words, and I was like, what is this? Like, who is making the mistake? Is it the phonetician that's making the mistake, or like what's happening in the model? And it's not the case that model does like a lot of, their model also produces some invalid outputs, so like some complete gibberish, but those are actually rarer. And so we realized, okay, innovation is the feature of learning in these networks. So how do you know that the model really learned words? Is because, again, we have this causal way to show that, right? So when you have the model, it learns to represent word 1 with 100, word 2 with 010, and so on. And when you again stretch those variables, the latent variables, to extreme values, you get a categorical output of a single word per code. Okay, so that's the best you can possibly imagine. And that addresses one of the issues that people had with connectionism. Said, oh, connectionism can never be categorical. With this technique, we almost show that for some cases it's like completely categorical, right? So here we have we trained the model on 8 words, three features, so 8 binary codes. And say ask is encoded with 15, 15, 0, dark is encoded with 15, 15, 15, water is encoded with 0, 15, 0, and so on. And the outputs are nearly categorical. So you can really test the underlying representation of each individual neuron, right? So now you have a way to take an individual neuron and test its underlying representation. And the nice thing is you have a model of both production and perception. Right? You can take that trained generator and say, give me all the words for code 015, 0 and give you a single word. And then what we did here in this paper is you can take unobserved timid and feed it to the Q network, and the Q network will classify those words with the same codes, although the Q network never saw timid at all, right? The Q network never saw timid at all. It only saw generated outputs, and it's able to basically classify predictably. So you have a model of generation, of production, and a model of classification or perception. And you have information that ties them together. This will also be in the collab, and the model learns compositionally, which is really nice, right? So 100 is word 1, I don't know, greasy or oily or suit. 010 is word 2. So this kind of codes encode words, but then features encode sublexical structure, right? So the model has a way to encode that suit and greasy both have an S there, right? So for example, it takes one bit to encode sublexical structure, right? So binary code is compositional, words are compositional, and it finds a way to match compositionality between codes, and so that's actually super useful to do phonological research as well. Okay, so here is maybe a little too technical. We show that the words are represented with binary codes. Subcode, these individual bits represent, say, presence of S. And then again, you can manually turn S from, manually make S disappear or appear from the output. Okay, so now onto an illustration of what kind of processes you can model in morphophonology with this. And then we're going to get to syntax, and then we're going to go to collabs. But any questions so far? Yes.
It's like when the S is used as like aspiration show up, then like is that sort of also
we didn't really test that. I'm going to talk about reduplication and might answer your questions, but definitely something that can be tested, right? So if you force an S, will something else happen? We did that, I think, actually with vowel harmony, and it did happen, but not, we didn't test specifically that the aspiration rule.
Question.
Yes. And they're more difficult to learn than local dependencies. We've shown that. And actually the rate of learning with humans are super similar. So that's on the next slide. But okay, so we can model, the first thing we model then is reduplication, because it's the holy grail of phonology. And so just to give you an example of what kind of stuff you can model, right? So reduplication is like it's been disputed for a long time, because Marcus in 1999 says it cannot be learned at all by neural nets. And kids are, full of reduplication. So the idea is neural nets are bad models of kids. Now, since Marcus 99, a lot of models have shown that reduplication can be learned, but all those models are continuous models, right? So they do not work with raw data. So what we did, and this is an illustration of how to use these models as well, we had a speaker record about 1,000 reduplicated and unreduplicated form, like Thara, Tithara, Dira, Didira, Nira, Ninira. That was in 2000, maybe 2001. Now you don't have a speaker anymore. You can have 11 labs and generate whatever toy data you want and train the models on whatever toy data you want. Back in the day, we still worked with humans. And then Sira, unreduplicated, right? So, and we actually didn't have any fricatives reduplicated. So fricatives were always unreduplicated. The rest was reduplicated. So this is the a toy example you can make to test reduplication. Now, this illustrates just how much more difficult it is to model reduplication from raw data, right? All models of reduplication work with characters. What we did here is we worked with raw data. You see, the network needs to learn that this is a reduplicated form of this, and this is a reduplicated form of this. Much, much more difficult. Okay, so what you do is you take our model, you have a folder of unreduplicated and reduplicated random waveforms, right? And you train the model, and then you have a generator. You give generators two codes, right? 1, 0 and 0, 1. And the rest is latent space randomly uniformly distributed. And you hope that the network will learn that 1, 0 is reduplicated and 0, 1 is unreduplicated, or or vice versa. So this is what the network gets. And it's true, when you don't then go and generate, 1, 0 gives you only 20% of reduplicated forms. 0, 1 gives you 60% of reduplicated forms. Again, our technique with extreme values, which kind of tests the underlying representation of this code. If you set the codes to 5, 0 and 0, 5 instead of 1, 0 and 0, 1, you'll get near categorical levels of reduplication and reduplication. What is even better, though, is that you can, again, force reduplication, right? So not only are these just unpaired reduplicated and bare stems or forms, you can take one output, set the code value from interpolate code value from 1, 0 to 0, 1, and the output will gradually become reduplicated with predictable nice reduplication, right? So Pira becomes Pipira, Nala becomes Nanala, and so on. So now you have basically a model of reduplication in a very causal in a very causal way, and this happens over and over again. And you can backtest these models, right? You can say, what if I asked you that you be fricative initial word and also be reduplicated, something that the network didn't see before? What you do is, okay, I know that C1, so the 0, 1 and 1, 0 represents reduplication. What I do is I look at the latent space, the Z variables, and with that regression, I found which Z variable encodes presence of S, right? Frication. And I stretch both to extreme values. So this is, again, the question of disentanglement, right? So when I ask which variables out of 100 represent S the most, you see one has a big peak, and then the rest is kind of gradual decline. We see this over and over again, actually even better than this. Usually, oftentimes the first most predictive variable is much higher than the rest. And then we say, what will happen if I say be reduplicated and BS initial word? If the network learned reduplication, it'll say Sasara. If it didn't, it'll just recombine, right? If it learns the concatenative process, not the identity-based process, it'll just recombine. And we found twice, actually, because we replicated the experiment, that the network nicely generates as reduplication. So it says Sasaya, CCU, and so on. Again, yeah, we replicated the reduplication experiment. Other things you can do is you test non-local phenomena. This is an example where we tested a vowel harmony on a toy data. I'm not going to go into details, but the thing is that we also tested the same toy data on human learners. So you can basically train artificial grammar learning experiments on humans, use the same data to train these models. The nice thing about these models is they don't require tons of data, okay? Even a couple of 100 data points is useful.
Oh,
No.
no, it's not.
He used to be huge. It's not huge anymore. But yeah, okay, it's like 5,000 tokens or 3,000 tokens. But well, so we got very interpretable, nice results on 1,000 total tokens of the replication experiment. This one is about 300 tokens. So you don't need a ton of data. You literally can use the same data from your artificial grammar learning experiments to train these models. They're not transformers. They're not as data hungry at all. Actually, this is surprising. It was surprising to me as well. And then one nice thing is that you can also learn progression of learning, right? So you can say, okay, at 7,000 training steps, the network outputs 0, which violates this data. Not important. No, it's not important why, but like, 2,000 steps later, the network repairs that violation in a linguistically interpretable way. So Zilo goes into Sulo, and then Sulo goes into Fulo, and Fulo goes into Tulo as the model is learning. So basically, there's a way to test the models as it's being progressively trained. Okay, so that's nice. And also, you can compare human and and these models' performance. Let's say something like a task like vowel harmony, right? So we happen to do this experiment for on humans in artificial grammar learning tasks. It was like plural, right? Martian plural, one object, 2 objects, 1 form, 2 form, the other form. And the network and the rates of harmony applications that the network and humans learn are roughly equivalent. And you can do this kind of comparison in behavioral learning between human artificial grammar learning experiments and the models very easily. So these are some external labs that that used our models and got really good results. Jingyi, as I mentioned, from Ohio, had this paper. It actually was best area chair paper in ACL in 2023, where they tested the French nasalization. Sneha and the team tested it on Assamese vowel harmony. But basically, any linguistic process you can think of can be tested, because now you have basically a single unit that represents something linguistically meaningful that you can causally manipulate. Okay, questions before we get into looking inside those networks and neural interpretability? Yes. Stress. Yeah, we haven't really tried that. It didn't have any problems with the current stress, but it's true that the reduplicated syllable is reduced, and when it does, so this is the model's output, right? You see se, reduplicated syllable se, and then the rest of the word. Okay, this is human recording, which was withheld from the data, just as a comparison how similar these outputs are. And you see that in human recording, in real data, the reduplicated syllable is reduced, or the vowel is reduced. And so is here, but that's because the network learned that the vowel of reduplication is reduced. We also have interesting work on syntax of this. The other thing is that it's really interesting to model tones with these networks, because you can look inside them and see how exactly the model turns a symbol into a tone, and you can manipulate them and then do all sorts of comparison with human brain recordings. So yeah, that's definitely possible. Yes. Yeah, that's actually looking forward into this part, where we will talk about how the network transform a single symbol, a representation of a duplication, into the actual waveform. And the short answer is yes, but more in a neural processing way than maybe in linguistic way. So so this is so this is how the generator looks like. It has 100 latent variables, and then there's a fully connected layer, and then there's a bunch of convolution layers. Okay, so what we show is that these layers add high frequency stuff like format structure, whereas these layers learn low frequency stuff such as envelope, acoustic envelope. So there's definitely distribution in what these what different layers encode. So you definitely have a layer-wise representation of different phonetic categories that really nicely parallels the way we process speech in the brain. So Alan will talk about comparison between our brainstem and these networks. But this is more maybe phonetic information. What we haven't really tested is whether something like nasalization is encoded at a different hierarchy or say segmental stuff. I think at the symbolic level, everything is equal, but different, acoustic parameters get encoded differently. Sorry? Yes. Well, it was created in 1991. For that period, it was very large and state of the art. Okay, should we move to collabs? If you want to follow what we'll do, please open the website and open the collabs. So the collabs are available here. Home, updates, collabs. And the first one will, Bruno will walk you over what these models are, how to train them, how does the code look like. But the take-home message is that very simple to train and actually fun to play with.
All right, so if you have this open, the first thing you should do is create a copy so that you're not like editing the so that's what I'm going to do right now as well. So I have this as a backup in case something goes wrong. So go here and then click save a copy in Drive.
You should also save a copy of the folder, the LSA. It's fun, they're all viewers, something like that.
Sorry?
They're all just viewers.
Okay, yeah. Well, I see some people with laptops.
Yeah. No, I mean the viewer, the permission. They don't have.
Oh, okay, I see. Anyway, in that case, I won't like. That's how you do it if you wanted to do it. Anyway.
Do you need to like add the file to your drive, like the LSA job? I think it's that way.
Where is it?
I think it's just in the file website.
Alright.
Yeah, like you just like right click the name of it and then add it to it.
Right.
Here.
So I think this organize and now add shortcut.
Okay.
That's what you need to do if you actually want to follow this online. Okay.
All right, so we've heard a lot about like various things these models can do. So the purpose of this section is kind of to get an intuition about like what the code actually looks like, what's actually going on, like what are latent variables. So and if you're new to deep learning, a lot of this itself will be kind of information overload. So don't worry if you don't get everything. This more serves as like a starting point. So you can take this code and start playing around with it yourself. So part one, I'm going to be training a toy model, or showing how one is trained. So the kind of model that hangs over all of this is ciwGAN, which we've been introduced to. But for the toy model, we're just going to be doing the generator and the discriminator. And then we're going to do stuff with the Q network later. So the reason I'm demonstrating a toy model is, if you run the code yourself, it's kind of fast to train, and I train it on like non-linguistic data. That's where you can see the patterns emerge easily. And it's sort of easier to get an intuition about what the coding framework looks like. So I'm not going to go line by line through all the code, but this is like what a generator would look like in a PyTorch class. This is like the forward pass, so the sequence of functions that like compute, that take an input, they take as input the latent variables, and then sequentially they produce different transformations on each vector until you end up with an output, a waveform output. So if you were to run this model untrained, you would get something like this. It's completely like noisy gibberish. So that's the generator. Here's the discriminator, or the architecture of the discriminator. So you'll notice here, oh, sorry. So the discriminator takes as its input outputs from the generator, and then it say takes 10 outputs, and then it outputs 10 scores. So the generator's goal is to maximize these scores. So again, the point of this is just to kind of show like the nitty-gritty of what this actually looks like when you're using it, as opposed to when you're looking at a diagram and kind of imagining what's going on. Yeah, anyone with questions, please.
Also, the nice thing about this is that with some basic knowledge of PyTorch or TensorFlow, you can actually play with the architecture themselves and, you know, change training objectives or change training settings, or, you know, embed the generators into sequences of generators and stuff like that, which is not the case anymore kind of with LLMs, because they're so big and off the shelf that, and oftentimes also proprietary, that you cannot really play with. So actually, with some basic training, you can create new architectures for the purpose of this kind of research.
Yeah, and I think the best way to learn is by often kind of the barrier to entry is just getting things to work to begin with, and you like try to do something and then it doesn't work and you give up. So I think like the best way to learn is, if you have something that already works, just like tweaking with it and playing with it. And that's how you kind of understand what's going on, and B, can come up with new ideas about why things are a certain way in the model. Why does it model certain linguistic phenomenon a certain way and others another way? Yeah. Yeah. It could be that this toy model isn't coded as dynamically as it should be. So if you do it, so it could be a bug in the code or something. Yeah, it could be that there's some hard-coded dimensions, yeah. But basically, conceptually, what's key to understand is that the latent variables are just a bunch of inputs into the model. So I guess I'll go through how this model is trained. And again, I'm not going to go line by line. It's possible that some things here are not optimal. It's more for demonstration purposes. So you could have a training data that looks like this. So this is like training data that I made that's like really dumb. It's just noise concatenated with silence. And then I vary the size of the relative size of the noise and the silence. So this is like an imaginary language where you have like shh or shh and more silence within the kind of confines of the output. So you're just varying the duration of the noise. So the training objective is, this is what the discriminator sees. This discriminator sees these like ground truth examples of training. And the generator wants to produce stuff that looks like this, that will fool the discriminator into thinking that, into classifying these as coming from the real data. So if you run this, another reason I use the toy model is just because it's the models that you saw before take a lot of computing power and a long time to train. So here it's easy to get a result in very few training steps. So this would take like 2 minutes maybe to train, and then you can evaluate what the generator produces. So it hasn't like learned a lot. There's not a lot of variability in these outputs, but it does learn some general property, which is that there's more amplitude at the beginning versus at the end of the signal. And also point you to this. This is the input vector, so this is the latent space. So each output corresponds to a single input. And the input consists of 10 values, and these are the latent variables. So it's just that Z vector that's input produces a particular output. So yeah, I produce a bunch of those. So this is code for like holding constant an input and then changing one variable. So here I change the variable with index 5 and see whether interpolating it, like incrementally increasing or decreasing it, changes what the output looks like. So here I start off with a negative 100, and then I go to negative 5, negative 2, negative 1. And there's like, here there's fairly subtle changes, but you can see like the slope of the cone kind of, in this case, is changing. And again, this is very early in training, so and you can play around with the parameters and maybe you'll get more or less interesting results. But this is like with relatively very, very few training steps. So if you train this for a lot longer, you'd end up with things that look more or less like the training data. Another thing I wanted to show is how to evaluate the discriminator. So remember the discriminator, what it does is it takes as input like a batch of training data or a batch of generated samples, and its goal is to correctly assign high scores to the training data and low scores to the generated data. So you can also give it test data, like data it hasn't seen before, and then evaluate like what kind of properties it's learning. So here I gave it something where there's silence first, and then this is silence last, which is like the training data, random noise, and then also the generated outputs that you saw. And so you can plot the distributions of scores that it gives each of these categories of sounds. So this kind of goes to the earlier question about like artifacts. So here you'll see that like this is the distribution of the training like sounds, the distribution of scores, and this is the distribution of scores for the generated outputs. So you can see that the generator really isn't fooling the discriminator, but it's still doing enough to make it far better than like the silence first samples. So it's still learning some property. Does that make sense?
This is all like just trained on toy.
Yeah.
Just for you to kind of get a understanding, a simplified understanding of the model.
Yeah.
We're gonna go to the real data now, right?
Yeah, so now we're gonna go to the real data.
Do you have any questions about it?
Yeah.
So there's a little bit of technicalities behind convolutional neural nets. And you know, any interest in machine learning textbook will tell you how they are. But if you're interested in exactly what they do, we'll figure it out. We'll go over. And when in the second part of it, Alan speak, we're gonna basically look inside the networks layer by layer, see what they do.
Okay.
Whether you've done any kind of experimentation with training kind of like an autoencoder to convert the training data into the feature space that goes into the physics model, whether that might help remedy this issue.
No, I think we have.
Okay.
The real data. So this is actually useful code if you want to do research. You just have a folder, you train the model for about 2 days, roughly. Depends on how fast your cars are. And then you do the kind of analysis by manipulating those single variables.
Yeah. Wait, how much time do we have?
So to the end of the first, we have 10 minutes.
Okay.
Then we'll go to the middle part in the second.
Yeah. So this is what like the real code looks like. And things shouldn't be hard coded here. But so again, you can play around with this on your own, and the idea is again to sort of get an intuition about what's really going on under the hood. So here's the forward pass where you get some Z vector as an input, and then it outputs some waveform. And you can also output intermediate layers. You could save those and then plot like what is the first convolutional layer output, what is the second convolutional layer output. So first I'm going to demonstrate like that like latent space interpolation that we saw earlier. So this is a ciwGAN trained on 9 lexical items. So basically it's optimized to map a particular one-hot encoding that it's initialized with to a particular lexical output. So again, what that looks like is just like this is the input into the network, in addition to a bunch of random noise variables. But basically the network gets this as an input and it wants to transmit this information to the Q network. And given the training data consists of 9 lexical items, the network learns that the best way to accomplish that task is to assign a latent each one-hot encoding to a particular lexical item. So I don't know if this will play. Hopefully it works when you do this on your own. And if you were to, yeah. So yeah, each one hot encoding input outputs a separate word. So this I think is like greasy or something. So that means that the network learns like accomplishes the training objective. Or the way that it accomplishes the training objective is to encode to ensure that a particular one hot encoding results in a particular word. That's not necessarily how it has to be every time. You could make it modify the training objective in certain ways to like incentivize it to learn other things, but that's what we see here. And then you could like test what the effect on the output is of holding constant all the other variables and just increasing that one variable. So that's another way of evaluating what the generator has learned and kind of seeing whether it maps the like sea of linguistic variability that's in the training data, whether it sort of maps it systematically to particular variables. There's other things you can do, which I won't go too much into. You can access trained weights from the model. So in the next section, I'll actually show like recent work we've done that you can use these weights in interesting ways to evaluate the model. And so this is just one thing. You can see like the average absolute weights of some variables are a lot higher than other variables. In this case, it's the latent codes that have higher average magnitudes of weights than all the other variables. So so that's sort of consistent with the training objective where it's like the value of the latent code is being scaled by higher values than the other variables. So the key takeaway is just that there's a bunch of things you can do to evaluate these models, and there's flexibility both in assembling these models and in the things you can do to evaluate them. So there's a bunch of different areas you can explore to answer different questions.
I should say that actually, this kind of work is not only linguistically interesting, but also interesting from the perspective of machine learning. Because CNNs are one of the basic architectures in machine learning, and while you often hear about transformers, pretty much every architecture that works with raw data probably still has CNN layer. Like even the Whisper and like or Wave2Vec, all those speech models that are based on transformers have a first layer that is a convolutional neural net. And you know, understanding how these models work is super consequential and interesting. So actually at the beginning when Alan and I started doing this work, it was mostly machine learning venues and journals who were interested, and linguists were not as interested because it's so difficult to say anything about how these models learn. And having linguistic data and our understanding of like, you know, symbolic representations and stuff like that is super useful to interpret these models. And so a lot of the initial work was actually published in engineering journals and venues as opposed to linguistics. But because it's, you know, it's such a valuable, you know, thing to make advances in understanding how the models learn. And a lot of the work on AI interpretability is done on computer vision, and comparatively, you know, much less is work done on speech or audio. But the nice thing about audio is that it's monodimensional. And oftentimes when you analyze these models, you add dimensions when you visualize or analyze them. And so if you start with a single dimension, it's much better because you can add one dimension more and interpret these models better. So that's something we'll continue with in the second part of the workshop. But yeah, so just to, you know, let you know that the machine learning world is interested in this. They're sometimes even working on it.
Yeah. All right, in the last 3 minutes, I'll just go through another thing that Gasper showed earlier is you can if you give the model the same input, but vary like the training steps from which the weights of the model were imported, so vary the checkpoints. So this is the model like after 6,200 steps, this is 12,400 steps. So you can give the same input to each of these checkpoints and then see what it produces at each of these stages in training. So this is a network I trained on like VCV words like ababa or something, except that I introduced like a rule where there has to be, if there's one fricative, the other sound can't be a fricative. So these are the vowels, these are like the consonants. So the sound doesn't work, but you can take my word for it that near the beginning, these two both sound exactly like fricatives. And then it's only later in training that like these still sound like fricatives, these still sound like fricatives. Then here you hear a clear fricative and a clear voiceless stop. So you can pretty easily explore like the training dynamics over time and like generate predictions and maybe fit it to human data, like how do humans learn over time? And then another just like technical tip, you don't need to use like a generator or a discriminator as its own function. You can break it up into like mini functions of the layers, and that's makes it really easy and flexible to actually like access the information that you want. So this is the code to do that. And yeah, any questions?
Hi everyone, my name is Jin Yichen. I am from the Ohio State University. I'm going to present how we use categorical info waveGAN to do our project exploring how generative adversarial networks learn phonological representation. So in this paper, we want to study how machine learning model capture language feature if we train it in a way that mimic human learning process. And then ciwGAN, the categorical info waveGAN, provide us a very good tools to explore the phonological system and how the features are constructed in different languages. So for the motivation, we already know that there's no obvious mapping between sounds and the category in the feature system, right? So this kind of connection is very abstract, but we want to study that. Then we need a tool to capture these kinds of connection, right? So ciwGAN provide us, we can use ciwGAN as a tool to study this. So for the research question, we want to know, are feature system cognitively real or not? If they are real, how can these feature system learned, right? So for this part, if we are able to train a machine learning model which mimic language learning process, and then we find when we find the machine learning model also have similar feature system, then we can answer this question, right? We can know that the feature system could be real. And for the second question, what patterns in the data distributionally lead to particular feature system? So in order to answer this question, we can also use the machine learning model, the categorical info wave GAN. The way that we use is we can design different training data sets. So the distribution of the training data sets can be different. And then we can study how would these different training data sets distribution can affect the learning results of the model. Okay, so this is what we want to study in the project. And we can skip this because we already learned how ciwGAN do. And in our case, we specifically focus on two languages, French and English. And then we already know that French has contrastive nasal vowel. English does not have contrastive nasal vowel, although we use nasal, we have vowels that have some nasal feature, but they are not contrastive, right? So from the language case, we already know English and French have very different nasal system on the vowel and also on the consonant. Then based on this spatial feature, we train ciwGAN and see how whether ciwGAN can capture this nasal feature, and then how would we get, like, what kinds of data distribution will we need to make ciwGAN learn such feature. Okay. So the training data sets for English, we just use TIMID, and French use ciwGAN French speech synthesis database. So for the distribution, we have this one is we take the entire data set and then we separate each audio file into a syllabus. So we have vowel plus oral consonant, vowel plus nasal consonant, and the distribution is about 64% of oral vowel, oral consonant, 36% oral vowel plus nasal consonant. Okay, but for French, because they have contrastive nasal vowel, so we have different type of syllable. So we have nasal vowel plus oral consonant. We have nasal vowel plus nasal consonants, oral vowel plus oral consonant, oral vowel plus nasal consonant. Okay, so this is our training data set. And we train the ciwGAN and use the trained model to generate the audios. And then because we generate some audios and we want to know which audio have nasal feature, nasal sounds, right? Then we use a pre-trained supervised CNN model to annotate the phonetic, the IPA label on the generated audios. And after we get that, we know which audio have some nasal sounds on the vowel, have some nasal sounds on the consonant. Then we run a linear regression to find out which latent variable in ciwGAN are directly connect to this nasal feature. Okay, and we pick the top 5 latent variables, and we do some experiments. Okay, for the English experiment, we first use a single latent variable. So by using the linear regression, we found out some latent variables that are associated with nasal feature. But we pick up the top 2 latent variables. Top 5 latent variables, and then manipulate them. And then what we find is 2 latent variables show independent control of the nasal consonants. So that means by manipulating that 2 latent variables, we can control the occurrence of nasal consonants. We can make the sounds into oral consonants and also make the sounds into nasal consonant. Okay, but for the nasal vowel, we cannot find out any latent variables that are associated that can be used to control the nasal vowel feature independently. Okay, and for the interactive features, so for this experiment, we manipulate two latent variables at the same time. And then we find that by concurrently manipulate the two latent variables, associate to the nasal vowels, and also manipulate the two latent variables that associate to the nasal consonants. We find that there's no clear interaction between the two latent variables. So only one single latent variable shows major control on the English nasal coda. And then no latent variable is found to control the occurrence of the nasal vowel. And for the vowel nasality, it tends to be occur with the nasal consonant. So whenever we have nasal vowel, it must have a nasal consonant next to it, right? And then by doing these experiments, we found that the ciwGAN encodes English nasal vowel as a non-contrastive phonetic feature, which is like match with our language system, right? English do not have a contrastive nasal vowel, and our machine model do capture this, okay? For French experiment, we found some interaction between the two latent variables in controlling the occurrence of nasal vowel and also control the nasal consonant, okay? And we also found latent variable that can only control the French nasal vowel, and also latent variable that can only control French nasal vowel, right? So all these features, all these results show that ciwGAN encode French nasal vowel as a contrastive phonological feature. So by getting all these results, we know that first, ciwGAN can be a very good model to capture a language feature system. We have the same feature results that align with our human language system. We train the model on English vowel sounds without any labeling, and the model can figure out the exact sound system, sound nasal system in English. And when we train the model with French sounds without any labeling, the model can also figure out the nasal sound system in French and generate French vowels and French consonant sounds. Okay, so for the training data distribution, we find that different distribution of the nasal vowel and nasal consonant do affect our results. And for the conclusion, so we find that ciwGAN, we claim that ciwGAN can learn a clear interpretable representation system. But what we found in our results is ciwGAN, the latent variables representation actually have some feature conjunction, which means ciwGAN tends to use multiple latent variable to control a single sound feature. So in English nasal system. Okay, but by using ciwGAN, we are benefit with exploring the relationship between the nasal vowel and nasal consonants, and also we have a way to analyze how the connection between the underlying representation, like for example, our latent variables in ciwGAN, and the actual sounds that realize in our generated audio. Okay. And more things we learn is feature system are learnable from the data, because we can train model to generate sounds that are similar to human languages. And for our question, what affects the representation? We find that the contrastiveness of phonological phenomenon can affect the representation, and also the frequency of different syllable types in the data also affects the sounds representation. Okay, so that's all we found in our project by training ciwGAN to capture language sound feature. Thank you all for listening.
Hi everyone, I'm Sneha from the IIT Guwahati, India. I hope you are enjoying the tutorial. So I'm here to present our project on implementation of visual info fiwGAN on Assamese vowel harmony. Before diving into the experiment, I'd like to talk a bit about vowel harmony as a phonological process, why it is important to model its learnability from raw speech, and how this process is observed in our understudied language, Assamese. As we all know, vowel harmony is a complex phonological process, and it's observed in many languages where vowels within a word tend to be influenced by one another in terms of their phonetic properties. sorry like pardon my voice, I've got severe cold. Anyway, uh, the complexity of this process comes from its nature, that is, it's a widespread instance but nowhere near universal. So it also involves learning crucial factors like features, domains, directionality, iterativity, and opacity. The languages of the world show regular patterns of vowel harmony but also accommodates exceptions heavily. This nature makes it an interesting point to decipher how this process is learned by human infants. Earlier studies of learnability of harmony heavily relied on curated text data, but raw speech is an approximation of the input received by a child. Therefore, it's expected to be easy to infer the phonology of this process from readily available data. Our understudied language is Assamese, which is an Indo-Aryan language spoken across the state of Assam in the northeastern part of India. It is spoken by 15 million people according to the latest census of India. It has 20 consonants and 8 surface vowels. The vowel harmony process is Assamese, like any other language, is mainly focused on the aspects like feature of the trigger and the target vowel, directionality of the harmony, domain of harmony, iterative pattern, and also opacity. Now, these are crucial in learning the process, and we also aim to understand whether machine learning models do consider these aspects while learning from speech. When we talk about the feature, we mainly talk about the features of trigger and the target vowel. In Assamese, we have the plus I plus AT vowels like E and U, which act as the trigger vowels, and the trigger harmony of the minus I minus AT vowels like A, O, and U, and they turn into A, O, and U respectively. For example, we have this word here for belly, we have pet, where we have this minus I minus AT vowel. It becomes a plus I plus AT vowel like A whenever followed by another plus I plus AT vowel or the trigger vowel like U. So basically pet becomes petu. Same happens with pagal where O becomes O whenever followed by E. Then we have directionality at which the harmony triggers. So basically based on directionality, there are two types of harmony, regressive and progressive. Assamese shows regressive vowel harmony where the trigger vowel is always on the right side and it triggers harmony of the vowel on its left side. Now comes in then we have domain where we talk about the basically domain here also refers to the locality of the harmony. So we have local harmony and non-local harmony, right? So in local harmony, what happens? The trigger vowel targets only the immediately neighboring vowel for harmony changes, which is local harmony. And in non-local harmony, trigger vowel targets all the vowels in its vicinity, which is what happens in Assamese. So Assamese shows both local harmony as well as non-local harmony. Then we have the pattern of iterativity, which makes Assamese an interesting case study. So basically in Assamese, we see long distance iterative harmony, which means that the trigger vowel will trigger harmony changes of all the vowels on its left. It not only affects the immediately preceding vowel, but also the next, also the penultimate and the all the vowels on its left side. So it's called the long distance iterative harmony, and it's a rare phenomenon, and it makes Assamese really a special case study to study vowel harmony. And we also try to see whether the model is able to capture this long distance pattern. Then we have the opacity or the transparency in transparent vowel, which blocks harmony. And here we have a, which basically, even though it's a minus I minus eta vowel, it does block harmony and do not participate, except for these exceptions where we have like same vowel both in the suffix as well as in the root word. So having said that, so for our experiment, we used the feature info waveGAN architecture proposed by Begush in 2021 and Begush in 2022. We wanted to, for that, because we wanted to see not only feature learning but also emergence of lexical learning from the training. For our day training purpose, we trained the model on Assamese raw speech samples, for which we also created a manual speech dataset. The objective of our research was to model Assamese vowel harmony from speech data to understand to the extent to which the discrete categories related to vowel harmony can be captured by the model, and also to get an understanding of the model's behavior. So to create the manual speech dataset, we consulted with 15 native Eastern Assamese speakers from the campus, 8 females and 7 males between the ages of 18 to 35, and we recorded them at the institute's lab. Now the dataset looked like this. So basically, this is Moi Kobo Buli Kolo, which is basically I say X when translated to English, and we the harmonic and the non-harmonic sets words were underlined for our ease of understanding. They didn't know about it, so they just read it out, and we recorded the words, and then after that we sliced the target words from the sentences on chart manually. So to implement the model, since we had about 82 unique lexical items and 15 participants, we used around 4,800 tokens to train the model, and the latent space of the model had like 93 uniformly distributed random variables, 7 binary latent variables, and our batch size was about 64, and the model was trained for around 1050 epochs, which led to 77,700 steps of training, and each epoch generated 100 random outputs. We downloaded our data or the outputs after the 960 epochs of training, and at each epoch we analyzed 64 out of 100 outputs. Now we'd look at the results we obtained from the training. So based on the noise quality, 64 outputs were analyzed, and we categorized them in two parts. Like one is the novel items, and then there are the identical items. So among the 64 outputs, we had 29 novel items and 35 identical items. Now among the novel items, there were 20 innovative items, and which are also grammatical, and 9 of them were ungrammatical or not permitted in a language really. And then we had the identical items, which are identical to the training data set, and then we had the ungrammatical ones, which were totally ungrammatical. Uh, Interestingly, among the identical items, 25 had, like, all the items have had either locally or non-locally illicit vowel patterns, so they were not completely illicit. Now, these are some of the sample outputs which we got, sample outputs after the training the machine. So we had a training item named Prohori, and for after training we got yeah. Then we had the innovative items. So we got Korisua and Debeku, which were not in the training dataset and also do not exist uh, in Assamese lexicon. And but Korisua here, although Debeku doesn't have any lexical meaning in the language, Korisua here do form a compound word and is supportive of emergence of lexical learning. Then we have the ungrammatical outputs like so in the training data we had Podobi, but we got Podobi. Even though we see local harmonic patterns, the long distance was not captured. So that's why and it also is not permitted in the language. So we discard it as an ungrammatical output. Having said all that, so these were mostly manual tasks. So I listened to the outputs manually on Pratt and on Audacity, and then I also asked the Assamese speakers to listen to them and to let me know whatever they listen, whether they could make anything out of the noise. But to identify or to quantify what exactly is happening over there, uh, we did a statistical analysis where we analyzed the first three format values of of items in the training dataset as well as the outputs. So whatever we found in the training dataset was our baseline or the ground truth, and based on that we judged the outputs. So for harmonic and non-harmonic cases in the training dataset, we observed that the F1 value of the target vowel always dropped in the vicinity of the trigger vowel. So whenever a target vowel is going through harmonic changes, its F1 value was always significantly uh, sorry, significantly affected by the trigger vowel. But F2 and F3 was not that much hampered because it's a height harmony. So naturally F1 was mostly affected. Here we have a comparison between two samples, Podobi and Podobi, where it's just a pair. So Podobi is basically the training data, and Podobi is basically the output we got, and we see that wherever the harmony is happening, the F1 value drops a bit, goes slightly near to the trigger vowel, but whichever is not, like here we have all the vowels are targeted or go through harmonic changes, so it's somewhat near the trigger vowel. But in case of the machine generated output, we saw it's very high and mostly like very far away from the trigger vowel. So we say that this is not harmonic, and if it drops then it's harmonic. So this is how we categorized the or quantified the existence of harmony, tier harmony, and there are other sets as well. These are just the sample pairs. Then to understand at which direction does the harmony occur, we did uh, a linear mixed effects model analysis, where we saw that in case of the 8-tier harmony, it's always leftward. So its right to left regressive harmony was more significant than right to left harmony. And since we did not have much outputs to judge which direction the harmony is occurring, we could not do it on the outputs as well, but we are trying to generate more outputs to understand whether directionality or the regressive directionality is captured in the outputs. But we did find something interesting, which is the feature value is being learned by the model, because in the output set we see that as the V2 or the trigger vowel the vowel E has the highest coefficient. So we think that that the model is able to identify E, which is plus I plus ATR in the language itself, as a potential trigger vowel rather than other vowels. So now that we have the generator producing an output matching the stimulus we had earlier, we have also tried to visualize what exactly is going on inside the generator by looking at the feature maps of the feature maps of the architecture, and also it follows the interpretation technique proposed by Begush in 2022. We see that at layer 4 we get a human voice like spectrogram, and so basically the human audio quality like human like noise is being produced by the generator. We also then plotted the feature maps of all the 5 layers over time. And by averaging over the feature maps of each activation layer for the time series data, we see that we see spectral peaks, which is positive, but we're yet to see which latent variables are actually uh, contributing to learning the features, and also which acoustic features are exactly being learned on these layers. Uh, so, as I was saying, so we see that the model is able to compute long distance iterative vowel harmony, which was one of the crux of our experiment, and it we also see that it's able to identify which feature can be uh, the trigger vowel feature, and we see emergence of lexical learning, and we see that even though there are ungrammatical outputs, they have local harmony. So basically harmony is not it's can be identified by the model, but whether it's long distance or local, that is to be studied more. But we had lack of results with the opic vowel R, so we are still pondering over whether it's difficult to learn the non-frequent or irregular items by the model, just like just like infants do take them some time to understand the exceptions. So there are still some unsolved questions where we try to understand which acoustic features exactly does the generator extract from the audio, and how it encodes them in its layers. We also would like to understand which latent variable is the most responsible for the feature learning, which is a study is still going in under process, and we hope that once we understand how the hows and whys of these instances, it will be easier to decipher or to identify the processes involved in learning vowel harmony in SMEs. So this was my time. Thank you so much. Please reach out to me if you have any questions. Thank you.